Hello everyone and welcome to lesson 10, and the topic is ecology, and in this lesson we shall look at capture recapture method. Remember, in the previous lesson we looked at methods of estimating population of organisms. We looked at direct count method, where you just count organisms 1, 2, 3, 4 and so on. We looked at using aerial photography, and this time we want to look at capture recapture method. Sometimes it's called capture release recapture method. So this method is suitable for animals which are fast moving, organisms that move faster, that we cannot use the other two methods for such organisms. For example, rats or fish. Imagine if you are using aerial photograph for rats. By the time you set your camera, the rats have already disappeared. You cannot take the photo. So here we use this method, capture release recapture method. So what happens in this method? So what you do is very simple. The first thing you do, after identifying where the organisms are and you want to determine their population, for example, you want to determine the population of fish in a pond. What do? You set traps. You use environmental friendly traps, set them there, and then capture the organisms which can be trapped. After capturing them, count them. How many are they? Maybe they are 50, maybe they are 100. Count them. You can call that number n. After capturing them, you mark them. If they are fish, you can put some small tags on their operculum, so that the tag you put or the mark you use should not expose the organism to danger. At the same time, it should not limit the organism to move freely. So you can put a slight mark that you know, that you can easily identify, but again should not be harmful to the organism. After marking them, release them back to the same habitat, the same area, same pond. Then allow them to mix, maybe for 2-3 days. Then after, you go back, and in the same way again capture organisms from there randomly, using the same tool you used before. So you may realize that this time you have captured maybe slightly higher number or slightly less, depending on the trap. Well, you can call that number M. But among the ones you have captured for the second time, there may be some that had the marks for the first capture. The ones now you have recaptured for the second time, you can isolate them and count them, and then you can call them R. So simple as that. So what do you do now? You already have the number of organisms in the first capture. You have counted them and you know them, N. Then you also know the number of organisms that you have captured for the second time. In the second capture, you know them. And then you know the number of organisms whom you recaptured that bear the marks. So what do you do to compute the total population? So you can call the total population maybe P, population, and is equal to the number of organisms in the first capture, N, times the number of organisms in the second capture, M, divided by the number of organisms in the second capture that had the marks, R. That would be your total population. As simple as that. So in summary, if you want to establish the population of organisms using capture recapture method, this is what you do. If you want to capture if you want to estimate the populations, go and capture the organisms for the first time and count them, call them any letter, maybe N. Release them after marking them. The marks help you to identify. release them back. After some time, after you have estimated that now they have uniformly mixed with the rest, you again set your trap, capture them again for the second time, the second capture, and then count them. How many are they? Maybe 50, maybe 100. Call them M. But among those ones you have captured for a second time, there are those ones who appeared in the first time that have the marks. Isolate them and count them. Then you call them R, that particular group. Then if you want to determine the population now of that habitat, it is the number of organisms in the first capture, N, times the number in the second capture, M, divided by the number of those in the second capture that had the marks, R. That will be your population in that habitat. For example, 30 in the bush around the school, they were all marked with ink on the tails and then released. That was the number in the first capture, 30. After 3 days, 20 rats were caught from the same area, so 20 rats were the number in the second capture. Then 6 out of the 20 had the marks, so 6 were the ones who were recaptured in the second capture. Estimate the population of the rats. So using our formula, total population P is equal to the number of rats in the first capture, 30, times the number in the second capture, 20, divided by 6. 30 times 20 is 600. Divide by 6, you get 100. 100 is the population of rats in that bush. Finished. It means you have calculated, you now estimated the population. You can do the same for fish, you can do the same for grasshoppers and organisms of the same kind that are very mobile. Quite simple. Our only caution is that as you are capturing these organisms, take precaution, avoid damaging them, and also avoid putting marks that may limit organisms' movement or that may expose them to danger. Put simple marks. If it is a rats, just put small ink on the tail, just to mark with a marker. You can be able to identify them. If it is a fish, you can use a small tag on the gill cover that doesn't really expose them to danger. Great. So I know you can do this at home. Try it in the compound, try it around home. You can be able to identify an organism and then try to estimate their population using capture, release, recapture method. I know you can do it. Great. The other method is the quadrat. So this is a method used for small static organisms like plants or slow moving animals. So the quadrat in this time is used for very static organisms or very slowly moving organisms. You can use them for estimating population of grass in the field, in the football pitch. Quite simple, because you are sure these organisms will not run away. So what is a quadrat? It's a small square metallic or wooden frame. It can be 1 meter squared. You can make it at home locally using wood. You measure 100 centimeters squared. That is 1 meter squared. Then you make your quadrat. Then after which, the quadrat is thrown randomly anywhere. You can try it in the football pitch. Drop it in the goalpost, drop it in the middle, drop it on the side, drop it randomly. Every time you drop it, make sure you count all the organisms it encloses, all of those organisms which are there, all the plants that are there that you are targeting to count. After counting them, the members of that one species that you want, record them. Maybe there are 50 in the first, maybe there are 60 in the other, maybe there are 20 in another, maybe there are 50 in another one, maybe there are 25 in another. So you add all of them divided by the number of quadrats that you have dropped. There you'll be able to get the average population per square meter. So that will be the average population per square meter. Now if that football pitch is 100 square meters, so what do you do? If there are 50 organisms average per square meter, what about if it is 100 meters squared? what will be the population? So you extrapolate. If 1 meter is equal to 50, 1 meter squared, what about 100 meters squared? It will be 50 times 100. That will be your population of grass in the whole football pitch. So that is how we use the quadrat. Mwanguzi Nathan was trying to demonstrate here how you can do it. So that's how the quadrat looks like. And you can count those grasses. How many are there inside that quadrat? Count them, record. Then drop it again somewhere randomly. Drop it in another place randomly. You can drop it in 5 or 6 places within that area, within that compound of yours. And then in every place you have dropped, count how many they are. Maybe they are 10, 15, and so on. Then get the average. By adding all of them, divide by the number of the quadrat dropped. And then you can now use, that will be the number of organisms in 1 meter squared, if your quadrat is 1 meter squared. Then you can use that method to extrapolate for the whole size of the land that you have used. If it is a 100 meters squared, you can extrapolate. If it is 50 meters squared, you can extrapolate by simply referring that if 1 meter squared is equal to this number, what about 20 meters squared? What will it be? So you'll be able to determine the population of organisms in your area. Remember, this method is used for slow-moving organisms or static organisms, organisms that don't move. Don't use it for estimating population of cockroaches. Surely you will be disappointed. Don't use it for chicken, for rats. It may not work, but you can use it for grass and other static organisms that are small, that can easily be enclosed in the quadrat. That's great. So we have seen how we can estimate populations using direct count, aerial photograph, capture, release, recapture method, and then the quadrat method. That is good for you. You can also search for other methods that we can use for estimating populations of organisms. Well, now let's look at human populations. Who knows how many people are there today in the world? Well, they say about 7.3 billion people today in the world. So we have very many. Then Africa has about 1.4, 1.3 billion people. Then China also has about 1.3 billion people. Then Uganda about 40 to 45 million people. Those are human populations. Each country has its own population. But the whole world has about 7 billion people. That is the population of human beings in the world. So human populations grow continuously with no decrease. Remember the graph of population growth. There was a decrease at some point. But for human populations, they don't follow that graph. For them, they grow continuously without decreasing. And why? Why do human populations continuously grow? Well, this is because of the fact that there is an improvement in agriculture to produce enough food. So there is enough food. Surely, if there is enough food to eat, surely, why wouldn't you grow? Why wouldn't you produce? Then there is a development in medical care to control disease. There's a lot of research in medicine. And many of the diseases that used to affect humans are now well controlled. Some of them are even vaccinated against. Plague, polio, many other diseases are vaccinated, hepatitis B and the rest. So you'll find that organisms are able to live now much longer than it used to be before. There's also development in technology, and the quality of life is highly improved in humans. Those are the reasons why the human population is keeping on growing, and we do not expect it to reduce any soon. Human populations can therefore only be affected by catastrophes like earthquakes. Like you remember one of the world's most devastating effects of earthquakes that happened in the one called the tsunami that happened in South Asia that killed very many people. Droughts also affect them, famine and epidemics and pandemics. like coronavirus, that's affecting the whole world. So those are some of the things that may affect human populations. Otherwise, even with all those, still the human populations are increasing. You can see there the growth of the populations for humans in the world. Currently we are in 2020 there. So in about 1900, there are about 2 billion people. And then in about between 1950 and 2000, there are about 4 billion. Between 2000 and currently there are 7.8 billion people in 2020. That's estimated. By the end of 2020, there will be 7.8 billion people. And by 2050, it's expected that there will be 15.6 billion people in the world, an increase of about 7.3 billion from now. So by 2050, if you are going to live up to that time, then interact with 15.6 billion others in the world. So the population is going to increase continuously. So therefore, if you are there, please work very hard so that you can be able to compete favorably with the rest of the world. So human populations grow because of increase in technology, quality of life, because of improvement in agriculture to produce enough food, and because of good medical care. Now we have reduced the mortality rate for children and mothers. So children are able to live without dying because of the immunization and the medical care. And many other people are able to live longer. I'm told in Japan there's a growing population of the elderly people because of an increase in quality of life. So people are able to live longer and even reach very many years. Even people are reaching 100 years. Great. So there's something called carrying capacity. What is that? This is the total population of organisms the environment can support at a particular time without exhausting the resources. So the carrying capacity, I would just give you an example. Like in your classroom, if there are 100 desks, 100 seats, that means there will be 100 students seated there comfortably. So the carrying capacity of your class is 100. That is the maximum number the class can handle, the maximum number of students the class can handle. That is the carrying capacity of that classroom. So in the environment also, the environment has a carrying capacity. The maximum number of individuals or organisms of the same species that can be supported by the resources in that environment, the maximum possible number, is what we call the carrying capacity. Now, beyond the carrying capacity, there will be a strain on the resources. Yeah, there will be a challenge on the resources will be affected, and competition will be intense, and only the fit will survive. So the carrying capacity is the maximum number of organisms of the same species that a given habitat can support, or a given environment can support at a given time without affecting the resources. That's great. So there is something called patterns of population dispersion. You have seen that in some places the population is much, in other places there are very many people, other places there are very few. Some places there are very many trees, another place there are very few. That sounds interesting. What could be happening? That in some places there are very many individuals, other places there are few. So let's see. That is what we call patterns of population dispersion. How organisms are distributed in a given area is what we call population dispersion. It refers to the way individuals in a population are distributed in a particular area in which they are living. So we have quite a number of patterns, but here we have majorly three. We have one we call the clumped population distribution. Organisms are clustered together in groups. This may reflect a partially distribution of resources in an environment. So you can see in the clumped distribution, a clumped pattern, where there are many organisms, it means that's where the resources are. That is where the resources are found. So organisms tend to stay where there are resources, where they can find their livelihood. Then uniform distribution. Organisms are evenly spaced over an area. This is typical of environments in which organisms compete for a scarce resource like water. For example, in deserts, you can see that kind of uniform distribution. Then random distribution. Organisms have an unpredictable pattern of distribution. It is typical of species in which individuals don't act strongly. There's a little interaction, there's little competition, little what, so they are just distributed randomly wherever they find themselves. So members, those are the patterns of population distribution. So thank you very much for being good students in this lesson, and thank you for being attentive. Please continue to observe all the measures that we are using to stop coronavirus. Continue to obey your parents. Please stay at home until it is safe for you to move out. Stay safe and be blessed.